Yeah.
All right, shall we? So what is the formula for revenue? The formula for revenue is always the same. Go for it. Another. Price times quantity. Exactly right. So revenue is, and I'm going to put R of Q. We'll start using Q as a variable instead of X. So it's just price times quantity. Okay, so that's always our revenue formula. And what are the two common parts of cost? Generally speaking, cost is going to be CQ equals MQ plus B. What is the B part? And then I'd write MQ plus B to look like MX plus B in the linear equation. So what is the B? It's the y-intercept, but in terms of business, then your overhead, your fixed cost, yeah, anything like that. So that's your fixed cost. That's the cost that's unrelated to how many actual pizzas you make. It's the cost of paying for the well. And then what would the M stand for? Yeah, the cost of each individual thing that you made. There's a couple different ways we can refer to that. One is called the variable cost. And that makes sense because it's the cost that's literally attached to the variable Q. So that's your variable cost. We also call it marginal cost. It's the cost for that item. And marginal cost makes a lot of sense as a name because marginal starts with M, and M refers to the slope, which also refers to the marginal cost. I don't think historically that's why we use M for slope. M is not M because of marginal, but it's a happy coincidence. Okay, so that's cost. Those are the two parts. You've got your margin, your variable cost, your marginal cost, and you have the fixed cost, your overhead. And next, what does the demand function tell you? So now we have D of Q equals something. Right? What does that demand function tell you? Yes, the actual price. What we're computing with the demand function is price. And remember, so you input some quantity, like you say, I would like to this week sell 100 pizzas. Then you plug it into this demand function, which is the knowledge of a superhuman, omniscient being. And they say, hey, if you want to sell 100 pizzas this week, exactly, no more, no less, you should go ahead and charge $22.50 per pizza. And then exactly 100 people will show up and buy your pizza for $22.50. So demand function has that mystical quality that it claims omniscience about the people in your society. Okay, so that's what the demand function tells you. What does the x-intercept and the y-intercept of the demand function represent? And remember, this is very humorous. This is humorous. So first of all, demand function is always negatively sloping, whether it's a line or a parabola. The fact is it goes down. Because if you want more people to come buy your product, the price has to go down, right? So you should always expect a demand function to be going down, down, down. Because again, if you want more people to show up, you're going to have to lower the price to get the attention of people who otherwise wouldn't be interested. So what are these two humorous points on the demand function? What is the humor of the y-intercept, and what is the humor of the x-intercept? Who wants to do one of them? Which one do you want to do?
The y-intercept.
Okay, y-intercept means
It's the price where no one.
exactly. You just priced yourself out, right? It's too much. If you charge that much money, you just lost every single customer. Even the last customer. Imagine, there was one customer who would have paid a lot of money. Like, there would have been a lot of money. And then you raised the price just $10 more, and that last customer was like, forget you. I'm not buying your stupid product. Okay, yeah, so you just lost all your customers. Too much, no customers. Or, so then what's the x-intercept, Sarah? Exactly, even if it's free, right? Even if it's, oh no, not even if it's free, but because it's free, this is all the people who are interested. That's your maximum interest from society, right? So if you're just giving it away, that's how many people will actually show up. No more, right? There's no one else who's even interested. They're like, yeah, free? Yeah, I'm still not going. Okay, so those are the x-intercept and the y-intercept, and everything else in between is what we call business decisions, right? Everything else. All right, so what is the formula for profit, finally? So profit is, yeah, revenue minus cost. So RQ minus CQ. Oh, there we go. So those are all of the ideas that we talked about last time. Anyone have any random questions that popped up when you went home, you were thinking about the material, doing the homework, talking with your friends, your family, your dog, and you're like, hey, maybe you talk to your dog. Yes, sir? Oh, if you ever come up against a homework that's locked, just email me and I'll open it back up for you. So let's do that during break. Anybody else? Yeah, the same thing. Okay, just let me know. All right, so here we are. Today is February. Is this right? This doesn't look like today's. Today's the 7th. Okay, so that can't be right. Let me go back and look at the real calendar. Is that? Yeah, here we go. Okay, that makes a lot more sense. So today's February 7th. We'll now apply the power rule to all sorts of functions and answer interesting questions. And then your test will be on Tuesday. So did I already post the answer key for the practice test? I feel like I did. So no, you're saying? Well, let's just look. Everybody, if you go into Canvas, I'm sorry, this will take me a second. It takes so much time to log on. Gateway, Canvas. There we go. So if you go to Canvas, log on with your information. Don't log on with my information. That's not right. All right, so you go in, here's our class 213. You go to announcements, and then under announcements, I have a, oh, I didn't put it. Oh my goodness, I will put it. I will put the solutions to the practice test. I didn't email, did I email it to you? I didn't do anything like that. Okay, well, I will go ahead and do that right now during break. So just to make a note to myself here, I'm going to post solutions. That way you can look at all the solutions for the practice test. And then I will also respond to Fatima's and Sarah's more needs. Henry? Oh, you were just stretching. Okay, so I will do that, folks. I will post your solutions to the practice test. That way, I'll also post a blank copy of the practice test. So if you want to go home, do it again, you can. You can print out another copy. Does everyone have a copy of the practice test? Okay, that you do. Okay. All right, so yeah, that's your test on Tuesday. Now, what do you need to do to come to class on Tuesday to feel confident? Just do the practice test a couple of times. If you can do every problem in the practice test, then you're fine. Because the real test will be a smaller collection of problems from the practice test. Okay, so basically take the practice test, scratch out a whole bunch of problems, that's going to be your real test. So if you feel good about the practice test, you'll feel good about the real test. Of course, you can use a calculator during the test, and if during class you have any questions at all, you can come ask me. Now, I might not be able to answer your question. I might say, I can't answer that question. Or I'll say, it's a good question, let me tell everybody. And then I can clarify something for everyone. And no matter what, I will help you with your calculator. So if you come up to me with a calculator question, I will show you how to use your calculator, how to graph something, anything at all, I'll show you about your calculator, that's fine. Here we come here. Typically on the day of the test, just every time 2 or 3 students volunteer to bring food like pretzels and whatnot. So which of you want to be the volunteers this time? I'm just kidding. Nobody ever brings food. I don't think we're even allowed to have food in the room. But wouldn't that be a great world if every time you took a test, a couple students volunteered to bring food? All right, then I do have a joke for you. This is one of my wife's all-time favorite jokes. She just told it this morning, actually. So, student goes to the library and asks the librarian, "Where are your books on paranoia?" And the librarian says, good job, good job. All right, so the derivative. So, yeah, let's go ahead and dive right in here. Oh, I went way back. So we did the power rule, and now we have, there we go. Here we go. We're going to start doing some derivatives. Now, first of all, the most common notation that we will be using in this class is that given a function, which represents the height or the y value, then the derivative is f prime of x. So we'll just, that's usually the notation we'll use. But to be fair, there are other notations. So sometimes what you see is they give you the function as y equals. And if they give you the function as y equals, then the derivative is y prime. And then that would be, you know, the notation. Or, so I'm going to list some alternatives here. So it's either f of x equals and then f prime equals. Or they might even say, given the function y equals, the derivative is dy dx. And dy dx, that's, you know, might seem a little outlandish. Makes a lot of sense because d stands for delta, which is the Greek letter delta. And what they're actually doing here is they're referring to delta y over delta x, which is the change in y over the change in x, which is slope. So delta y over delta x is really slope, y2 minus y1 over x2 minus x1. And so by using this notation, we are referring to a secant slope between 2 points that have become infinitely close together. So even this notation, dy over dx, still means derivative. It still means the same thing as f prime of x or y prime or dy dx. They're all referring to tangent slope. So all of these notations mean the same thing. Just so you all know. So let's do some examples. Here we have our first function, f of x equals x to the 10th. One thing I'd like to do as we explore these functions is to actually look at the graphs of these functions. So for instance, with x to the 10th, go ahead and make a quick sketch. X to the 10th is an even power function, and as such, it simply looks like a parabola. So that's what the function looks like. And you can go ahead and do a quick analysis. What is the slope? The slope is negative, 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 0, positive, 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 positive. Just as our own understanding of what the derivative function should look like. Now everybody do the power rule. What would the power rule be? If the function is x to the 10, what is the power rule again? Yeah, 10x to the 9th. You multiply the exponent and subtract 1 from the exponent. Our mantra could be multiply, subtract 1. Multiply, subtract 1. So that becomes 10x to the 9th. Now, what does 10x to the 9th look like? If you graph 10x to the 9th, x to the 9th is an odd power, which looks like this. And sure enough, if you compare the slope values of your function, they are the y values of your derivative, right? Over here, the y values are negative because the slope values are negative. 0, the y value is 0. The slope is positive, y values are positive. Power rule gives a completely reasonable function that the y values represent the slope values. that could even be very helpful to write down. So the y values of f of x represent the slope values of f of x. And of course, you can write that backwards. The slope values of f of x are the y values of f prime of x. This would be really good to consider and say to yourself as often as possible until it becomes kind of muscle memory. Okay, so that's what the power rule gave us. Who'd like to do this one? Negative 7x squared. It would be, why subtract?
Oh, so that's a negative thing?
Huh?
X to the first.
Very good. And you can write to the first, or you can just leave it as x. So let's see, does this make sense? Is this a reasonable function? If you graph negative 7x squared, it would be an upside down parabola. And we could analyze that real quick. What are my slopes? My slopes were positive, 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 0, and then negative, negative, negative. So that's the original function. What does the derivative function look like? The derivative function is a negative that goes to the origin. So are the y values of the function the same as the slope values of the original? Sorry, are the y values of the derivative the same as the slope values of the original? And yes. On the left, the slope is positive. On the left, the y value. In the middle, 0. In the middle, the y value is 0. And on the right, the slopes are negative. And on the right, the y value. Notice here, I'm just doing little quick sketches, right? Incredibly accurate graphs. I don't have any coordinates on there, but do they contain all the information you need? Yeah. So these are good graphs to look at. How about this next one? H of x equals 1 over x cubed. Well, 1 over x cubed. Anybody know how to graph that one off the top of your head? Probably not. We don't have a lot of experience graphing reciprocal functions. You know, we know parabolas and we know cubics. Follow-up, whoops. I think I've already been saying this a lot, but one of the best first things you could do with any problem is go ahead and graph it. You want to actually see, so everybody you can see what you're looking at. It has this, what I call a starburst pattern. It kind of looks like a star shape. Anyway, so let's draw that. That's what our original function looks like. So, down like that, and then down like that. So what would we expect from our derivative formula? What are the slopes? Negative and negative. It's always negative. So whatever our function, or whatever our derivative function turns out to be, it better be always negative. So let's take a look. We want to do the derivative. I'm going to write it down. H of x equals 1 over x cubed. I'd like to do the derivative using the power rule. Now, here's the thing. You can only apply the power rule to an x that's numerator. We can't just do that. It would be incorrect to look at that and say the derivative is 1 over 3x squared. But you can't apply the power rule to an x that's in the denominator. Everything has to be raised up into the numerator. So how do we raise things up into the numerator? We have standard algebraic rules that we use for childhoods, and that is that x to the 1/2 is really the square root of x, and x to the negative net n is really 1 over x to the n, or stated the other way around, 1 over x to the n is really x to the n. So these are things we have to keep in mind. So before you even apply the power rule, you need x to a power. You're not allowed to apply the power rule to a square root. You have to change the square root into 1/2. And you're not allowed to apply the power rule to an x in the denominator. You have to push it up into the numerator. So how do we write 1 over x cubed? Yeah, x to the negative 3. Now you can feel free to apply the power rule. So multiply. So now I'm going to go down a line here. Prime of x equals multiply and then subtract. So negative 3 minus 1 is negative 4. Now, here's the silly thing. Okay. But it fits perfectly. In calculus, the algebra gets worse before it gets better. We started with 1 over x cubed. We had to algebraically manipulate it so that you have an x in the numerator. You do the derivative, and then you push it back down into the denominator from which it came. It's this whole little dance where your term begins in the denominator. You gotta push it up using algebra, perform your power rule, and then push it back to the denominator. That's the derivative, -3/c. And so that's just your little dance that you do. You're constantly applying these two little things. And what I'd like to tell you then is what your final answer should look like. The problem begins. This is what your looks like, or how your problem begins. But this is the space where you do your equation. This is the only way you can. You need extra number. Okay. Okay. So now let's. Does this thing always have a negative value or what you plug in for x? Because we just said that the slopes are always negative no matter what. So how do we know that this thing is negative? The top number is negative. Yeah, the power is even, so no matter what. So if I have something to the power, if I do a positive to the fourth power, it's positive. If I do a negative to the fourth power, so in the end, this thing is negative over a positive, which means no matter what, it's negative. So this matches. It's our expectation. Now, what's the only part of this graph that has no slope? Slope is undefined. Yeah, the y-axis right here. So if I plug x equals 0 into this function, what happens if I plug x equals 0 into that function? That's undefined. And if a function is undefined, the derivative is undefined. Because there is no slope. First of all, you can't even get to a tangent point. It's all the way up infinitely high. And therefore, there's no derivative. At x equals 0, what if I plug in x 0? It's also undefined. So this makes sense. It's negative everywhere except for x equals 0 where it's undefined. And this value everywhere except for x equals 0 where it's undefined. How does everyone feel about those examples? Okay, so what does our derivative function look like? Our original function, what's our derivative? It's always negative, right? What does -3/x to the fourth look like? We don't know. We're just little humans. I mean, to do this kind of stuff in your head, you have to have lots and lots of experience. -3/x to the fourth. There, that's what it looks like. So everybody draw a nice. And I think what we're doing here is building a really good habit of constantly looking at the function side by side with its derivative function. So this was, and this was. And you can check. On the left, the slopes are negative, the y values are negative. On the right, the slopes are negative, the y values are negative. The more you make that comparison, the more it'll have it memorized. Nope. That was 1, 2, 3, and now we're still on number 2. Apparently my numbering is everyone on this problem now?
Yeah.
It's what?
It would be like A, B, C.
Oh yeah, okay, that's what that was. All right. So what are we doing right now anyway? What are we doing? Oh yeah, we're doing. They're handing us a function. They're handing us some function, and you can take a look at that function. And you can say, well, that particular it's x to the 10th minus 2x to the 5th, but the end behavior is x to the 10th. So that makes it's going to be something like a parabola. That's essentially what I know. There could be a wiggle down there that we might need to really pay attention to. And in fact, we better do that. So let's take a look at this picture. Let's see what it looks like. So 3x to the 10th minus 2x to the 5th. 10 minus what? X to the 5th? Aha! You see that? A wiggle. Right? It wasn't just purely a parabola shape. There was a wiggle down here. And in fact, I don't know for sure what's happening here. Is there any more wiggles in here? I don't see any more wiggles in here. So it appears as though this graph comes down, 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 over that spot, and then over, down, 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 minimum, and then shoots back up again. So what is our slope? Negative, 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 0. Negative, 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 0. Let's all draw a picture. So let me erase my graph. Okay. So what happened? The graph came down and then over, hit a flat spot, and then down, a minimum, and then back up again. So does everyone have roughly that picture? So where did we have a slope of 0? There and there. Those were 0 slope points. Sometimes helps to draw that little slope indicator to remind yourself that you're not writing down a y value, you're writing down a slope value. So those were 2 flat points. Otherwise, what was our slope? Negative, 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 and then positive. So what should our graph look like of the derivative? What should the graph look like? Let's, at our 0 points. Anytime you have a 0 slope, what will you have on your graph? An x-intercept. Let's remind ourselves of that general rule. 0 slope means x-intercepts. And that makes sense because the slope over here is the y value over here. So 0 slope means I'd have to have a y value of 0, which is an x-intercept. So again, good thing to write down. Any flat spot, f of x, b, and x-intercept, time of x. And have nuggets at a time. I hope you write down these nuggets as well. A nugget, no. Running down nuggets up there, I hope you write it down too, unless you just got it. What should our graph now look like? To the left, the y value should be negative. And then what? The y should still be negative. What does that look like? Did it go boom? Did it back down? But then I have to go back up to the 0 point. Then what? Become positive. So what do you think? Did we just this graph? Do you think there's an error that when we actually take the derivative and graph it, it's going to anyone have confidence that this is calculus? Let's look. Let's do the actual f prime. We'd like to do this one. Thank you for your enthusiasm. You've answered a couple more. One, you weren't here for the power rule. One, real quick, power rule. Do the power rule, such as do 5x to the 4th. It's multiplied by the x. So you bring that out front, 4 times 5x, and then you subtract 1. That's how you take the derivative. The answer would be 20x cubed. The rule is you multiply the exponent out front, and then subtract from the exponent. So Juan, you try that. Multiply by the exponent out front, what do you get? 30. And then subtract 1 from the exponent. Very good. Do it again. Minus, multiply by the exponent out front. Very good. Yeah, so I mean, it's a very simple rule. By the exponent, subtract 1. Okay, so that's our. Now, let's look at it. Now, folks, this is the exciting part. Looking at graphs is the part. So the derivative was 30. Oh, I should have left it. Hold on. 3x to the 10th. We want to compare them side by side. Minus 2x to the 5th. There was the original. Now, 30 to the 9th. 10x to the 4th. Hey! Is it what we expect? Yeah, I mean, more. It looks like the graph we came up with. The derivative came up, it bounced back down, came down, went back up, and away it goes. So there we go. That's a nice comparison. The red is the original function. The blue is the derivative function. Do it again. So what does this graph look like? What's the end behavior of this graph? What's the global behavior of this graph? It's a parabola that's facing down. Facing down. But these extra terms means that there could be a what? Translation? Yeah. That's right, the parabola is translated. Well, yeah, and actually a good point. The parabola can't have any wiggles. The parabola is just a parabola. So it's just a translation. Very good job. So this is a parabola that's been translated. So let's see where it went. My two fingers not over there. So, but hey, I'm getting my 7 plus 4x minus 2x squared. Very good, there's our translation. It appears as though there's a maximum at 1,9, so we could go ahead and, do that in our graphs to make yourself fine. I have down here, the maximum was at 1,9. There it is, and that's our parabola. So what should our slope values be? They're going to go up positive, 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 0, negative, negative, negative. So what does that mean our derivative graph? But where's the x? There's a flat spot at x, so there's an x-intercept at 1. And then what should our y value be to the left? Positive. Then what should our y values be to the right? Negative. So that's what our derivative function should look like. So go ahead and do the derivative. The original function was plus 4x minus 2x squared. I'm going to call on you again to give you a little more. Go ahead and do the negative 2x squared part first. Yeah, just 4x. Now, this one, the 4x, sorry, there. So go ahead and do the 4x to the first. 4x to the, subtract 1. Yeah, 4x to the 0. And what is x to the 0? Yep, 1. Anything to the power of 0 is 1. And so that just goes away. It's just the number 4. So the derivative of any term, just a x variable with a number in front, the derivative is just the number. Now, what about 7? So this is 7x to the 0. Apply the same rule. Multiply by the exponent. 0 times 0, and then subtract 1. 0 minus 1 would be negative 1. And that doesn't matter because it's being multiplied by 0 anyway. It just goes. So, what's the lesson here? So everybody, 7 plus 4x minus 2. This is the only term you really have to do any thinking of. So you multiply by the 2, that's minus 4x. Anytime you have a linear term that is a number x, the derivative is true. Anytime you have a constant term, it just goes. So this is 4 minus 4. And sure, this mx plus b, I'm going to rewrite it, negative 4x plus 4. That's mx plus b. And what do we expect? A positive y-intercept and a negative sloping line. A positive y-intercept and a negative sloping line. I really hope that this whole exercise, the derivative alongside the original, is really important. Because I want you to think about these poor mathematicians, poor put-upon mathematicians in the 1600s and the 1700s. Did they have TI-82s? Did they have the Desmos? Did they have anything good in their lives? Answer, no. But now with calculus, could they figure out what looked like even though they didn't have a graphing calculator? Yeah, they actually had amazing sophisticated techniques to figure out what graphs look like, and no technology whatsoever. So that's what's so interesting about calculus. We need to finish that last problem. Yeah, plug in 2. So we're actually not quite done yet. We have to take our derivative. So our derivative was 4 minus 4x. So now I'm going to do f2. And I plug in 4 minus 4 times 2. So that's really 4, which is negative 4. So what does that mean? I'm going to go over to my graph here. On the one hand, f prime of 2 equals 4. I'm sorry, negative 4 means what? On my derivative graph, this was my input, output. That represents, right? Any input, output represents that graph. So now I go here to 2 and down to negative 4. That's a coordinate on my graph. So on the one hand, that's what that. On the derivative function, just basic input, output. It's a coordinate. But what does that mean about my original function? What happens if I go over to the coordinate 2 here? What about my graph at x equals 2 and 4? It's the slope right there. The slope right there is m equals down 4, right, down 4, right. So that's pretty interesting, okay? When you look at this function, f prime of 2 equals negative 4, it's telling you two things. It's telling you, under derivative formula, it's just telling you a coordinate, which is pretty basic information. But on your original function, it's not telling you the coordinate at 2, it's telling you the slope at x equals 2. How would I coordinate now? Where actually is that coordinate? I'd have to plug 2 into the original equation. If I plug 2 into that, that would be 7 plus 4 times 2 is 8 minus 2 times 4 is 8. So the actual coordinate is at 7. So that's very cool. This coordinate right here, gosh, I'm realizing how messy I am. I'll be better. That coordinate right there is the coordinate 2, 7, and it has a slope of -4. That's very sophisticated. That I want to know what my graph looks like, and since I have my function, I know the coordinate 2, 7. But now I find my derivative, I know the slope. So that's pretty powerful right there. That's what we're able to do right now. Given any function, we can consider the point, find the coordinate by plugging in an x value function, and find the slope of that point by plugging that same x value into the derivative function. And again, this is how those put upon mathematicians in the 1600s would make a graph. Because they could, for any given point, not only know where the coordinate is, they would also know the slope of that coordinate. And so they could make some pretty impressive graphs. Anyway, well, we don't really have all that many to do, which means we'll have time left over to talk about your practice. All right, so number 4. Look at that mess. Or is it a into that function? Look at that nice looking function. And what, Josh? It is a creative one. So if we're just looking at it, is it a parabola? Is it a straight line? We don't really know what this thing looks like. Yeah, it's weird. Correct. That thing's weird. Now, if you were 300 years ago and you want to know what the function would look like, you would have to make a table of values, do lots of values, and then make a graph and plot all sorts of points. You would look at all those points and you'd say, that's what that looks like. And that's how you did it a long time ago. Whereas if we have a table of values, we can just look at a graph. So let's go on over here and plug this in. 7 plus 8 over x plus, is it x squared? Yes. Okay. All right, so that, ooh, boy, that's nice. I've never seen such a nice looking. Consider, the function looks weird, but this graph looks kind of nice. So it comes down, it has a little, it goes back up. Now what's at the top right here? Am I going to find a maximum up there? Yeah, who knows? What do you think, maximum, or is this an asymptote? Yeah, I mean, how would I really know? I mean, couldn't I just keep it like this? How would I know if it finally is going to go and then come back down? Right, you can plug in 2. So these are good questions. Well, one question we ask is, what does a like? So there we go. Back to here, and we've got a big question. See what the graph looks like to the left? It's an asymptote. You know what it looks like to the right? It's an asymptote. And we have a nice little here. Well, what's at the top of that? That's the question. What's at the top? Right? If it's infinitely high, is there a top? No. So how could we go about answering the question, what's up there? Right. So if there were a top, then the derivative up there would be 0. You'd have a flat spot. Or, as Josh said, if you plug 2 into the function, was it 2? I said 0. Oh, yeah, 0. I think 0, they're approaching. If you plug in 0, if it's undefined, then it's an asymptote. But if you plug in 0 and it's an actual value, then you reach the top. So let's go ahead and probably you already answered it. Is it a maximum? Yeah, it looks like an asymptote. So let's draw a picture real quick. The minimum value is at, well, it's just a bit up a bit. We don't have to be incredibly precise about it. Well, let's draw a picture of what our looks like. Let's confirm our, so our graph, wait, it went like that, right? Very more or less. Yeah, not the best. Correct. There we go. So for sure, it's going this way like an asymptote. Comes down, up, comes that way like an asymptote. And the only question is what's going on up there. Well, the one flat spot we know for sure is here. So we got an m equals 0. Over here, the function is negative, decreasing. Right here, the function is positive, increasing. And then it's immediately negative forever. So now this is also interesting in terms of our ability to draw this graph. So we might as well answer the question, what happens up there? So if you take your function and plug in 0, you get 7 plus 0 over 0 squared, which is, yeah, that's undefined. Already kind of gives us a good clue that there's no maximum of that. It doesn't just go up and turn around and back, it goes up forever. Okay. We are going ahead and drawing what the graph should look like. What will the derivative look like? Do we have any x-intercepts? We'll plot the x-intercept first. We have one x-intercept here. And then what are the y values to the left? Negative, so it comes down that way. What are the y values to the right? Positive. However, as you're approaching 0, what are the y values to the right? Negative. And they stay negative. So maybe the function looks something like this. It's a pretty strange looking function. So now let's confirm our guess by actually taking the derivative. So how do we take the derivative? 7 plus 8 over x plus 3 over x squared. Push those variables up. We're going to do the power on a variable in the denominator. So now this is going to be 7 plus x to the negative 1. Is that right here? And then it will be 3x to the negative 2. So now these are just a bunch of normal terms. We can take the derivative using the power rule. What about 7? Nothing. Yeah, 0. So the 7 goes away. What's the derivative of 8x to the negative 1? So again, multiply, subtract. Negative 8x to the subtract. And then on this one, multiply. And negative 6x to the negative 3. Okay, very good. This is the worst part, right? Things get worse before they get better. So now we're all done. And by the way, this was still f of x. Now this is f prime of x. Very important that you show that we now jump. This was the original function. This is called rewriting the original function in a form that you can compute. Now we actually computed the derivative, and now we write final form. Final form is negative 8 over x squared minus 6 over x cubed. So just to show you what you can expect, first step was rewriting full form. Second step was to actually do the derivative. The third step was to write it in a clean form, right? Clean as a final answer. Here you go, this is my final answer. So it starts clean, you rewrite it so you can compute, you do the derivative, and you rewrite it. Those are the expectations. Okay, now what? Let's graph it. These are our expectations. I'm sorry, I can't really see it. Negative 8 over x squared. And negative 6 over x cubed. Let's turn that one off. Is that what we expected? Close. Not quite. There was a little dip. Actually, a whole lot worse. Yeah, this is very different from what we expected. I drew it going negative, but in fact, it comes negative and then it goes back up again. That was different from what we expected. But over here, that is what we expected. Doing the analysis we've been doing, figuring out that there was a dip there, we need to know a little more about how to know that. But overall, we had the general characteristics. Ourselves a pat on the back for figuring out what the derivative should look like. Okay. How does everyone feel about this? I realize we're layering up skills simultaneously. I mean, on the one hand, we're just doing the power rule. But on the other, I'm asking us to graph the original, analyze it in terms of slope, and then attempt to draw the derivative ourselves, and then confirm that by looking at the graph. So does this hurt your brain a little bit? Probably. It's a lot to go back and forth. So everyone try number 5. Yeah, everybody try number 5. I'll start off with the graph. What does 2 over x squared look like? So here's just 2 over x squared. So what would I like to do? I'd like you to start by drawing the graph. Yeah. Oh, we forgot to plug in. Silly me, were we supposed to plug in? Great, so f prime of would be -8 over 3 squared minus 6 over 3 cubed, which is 27. To be nice, we should find a common denominator and subtract. So the common denominator is 27, multiply top and bottom by 3. That gives us negative 20 27s minus 6 27s, which is negative 30 27s, which they're both divisible by 3, so that's negative 9, which is negative 1.11111. But should I compute my answer as a decimal? This is a slope, and slopes are fundamentally fractions. So we'll stop there. This is a slope. What I just found out was that on my original graph, if I go to x equals 3, what is the slope right there? Yeah. What else did I find out? On my derivative function, the coordinate is 3, negative 10 ninths. So on this graph, I'm saying the coordinate is 3, negative 10 ninths. So you'll notice here the negative 10 ninths is the slope of the function at x equals 3. Here the negative 10 ninths is the y value of the derivative at x equals 3. Isn't that interesting how the negative 10 ninths are 2 completely different ways? Of the negative 10 ninths is a slope. Of the second derivative function, the negative 10 ninths is the y value of the coordinate. Reminding me about that. Plugging in the 3. Like, let's say that you're out and about, and someone had this complex formula, and they said, hey, find prime of negative 3. Like, at the very least, you could be all cash about it and be like, it's a slope. Right? You know, and now at least you're in the ballpark. You're telling them what the answer is, they'd probably be like, cool, man, I got it. It is a slope. They said, find f of 3. You're like, that's important of my original function. And I'm like, cool, man, I got you. It is important. Okay, now we can proceed with doing number 5, and then we'll take a break. So what did our graph look like? It went up. Up that way. Right? Give yourself, you know, some slope indicators, pluses, minuses, zeros. Think about what the derivative should look like. And by the way, folks, we didn't say this. Your slope indicators can be pluses, minuses, zeros, and we should also indicate when it's undefined. But this is an asymptote. And what does that mean about this graph? There will also be an asymptote. So that's helpful that when you diagram your function with pluses, minuses, zeros, you could also diagram an asymptote and say, well, if my original function has an asymptote here, then this function will also have an asymptote. And then go ahead and take your function, which is what f of x equals 2 over x squared, and show those 4 steps. Remember those 4 steps. You start with the function, you rewrite it in usable form, you do the derivative, you rewrite it in clean form. Oh, this looks fun. That's yeah. There it is. Finish track 1. And what are those things? I think that continues to be positive. Yeah, it's very, very gradual, like the bunny hill, but then eventually it gets steep. And now this is very steep negative, and it stays negative forever. So a penny would keep going. Those looks positive. So you have that, turn it to that, and like that. Very good. Now just put your labels up front. So you actually know what you're looking at. Yeah, well, because it's tricky. It's tricky. So first of all, this was your function. This is also your function. It's right, f of x equals. Because all you did right there is you just rewrote it in a useful way. This is the actual derivative. So right, f prime of x equals. Good. Then this is still f prime of x. You just rewrote it. Okay. Now, so put another graph right below it. Good. So what we know now is that the y, so the slope values here should be the y values here. So all we really know, this is hard to do, all we really know is that to the right of the y-axis, the graph should be entirely positive. So only because I know what it's supposed to look like, go ahead and just sketch a little thing that looks like that. It has two asymptotes, one to the x-axis, one to the y-axis. Good. Now over here, the slopes are negative, so the y values won't be negative. So again, you can make a little sketch like that. Yeah. It's not always possible to do that. I admit this one you totally probably cannot do off the top of your head. Do that. Actually, let's look at it. There it is. Did you graph it or you just figured? How did you get this graph? Did you graph it on your calculator? Or you just kind of figured that's what it looked like? Nice. Yeah, very good. Let's go with that graphs. Okay, so wonderful. So let's check everybody's answers. Your 4 steps. So first you rewrite the function in a useful way, 2x to the negative 2. Then you actually compute the derivative by multiplying and subtracting negative 4x to the negative 3. Then you rewrite your derivative in a clean form, so that's negative 4 over x cubed. And now back to the graph, negative 4 over x cubed does in fact have an asymptote at 0 like we expected. And 4 over x cubed is the same graph as 4 over x, which is a reciprocal graph, an inverse graph. So it should end up looking like, everyone get this and this? Wait, because these slopes are positive, so the y value should be positive. These slopes are negative, so the y value should be negative. Yeah, is that the graph that people came up with? Now let's check. You know, we do have this technology at our disposal, so we can check. My function would be negative 4 over x cubed, and sure enough, that's what it is. Keeping in mind, these are just rough sketches that we're doing, right? Okay, 16. Great. Let's take a break. Time is 11:54. Let's come back at 12:04. Folks, I want you to know that you're all very sophisticated and you're rising to high expectations. I've never done it like this before, where we do the graph and then the derivative graph and then all this work. I normally just do the power rule and that's it. So I'm adding on more expectations to you than I've ever done to students in the past, and you all are doing great. Pretty sure. Where did we get to? All right. What's we're doing class? Sure. Okay, exactly on the dot. Let's do it. So, more excitement. Our next problem was 3 natural log of x. Now, we didn't talk about this at all. We have not talked about any other formulas besides the power rule. So I think now would be a good time to circle back and look at some formulas that your textbook gave you. So, in your textbook, at the beginning of this chapter, we'll go back to it here. Reference. I didn't bring that for you. I should. No. Yeah, I'll bring this for you. Okay, so we have a variety of derivative rules. I think we should go ahead and write them down. So we should put it here. I think you should get out a sheet of line paper. Let's get out a sheet of line paper and we'll review and write down all the derivative rules that are of interest to us. Now you'll notice on this particular page, they're giving us the derivative formulas in this notation of d dx. So the first thing we can do is just familiarize ourselves with this notation. That if I have a function, so that's the regular function, and then I apply to this function d dx. What that means is take the derivative of that function with respect to the variable x. And so the result of that operation would be f prime of x. So d dx is an operation that's telling you to do something. You don't have many of those operators in math. I mean, maybe a square root. The square root's kind of like that. It's saying like, hey, here's the number 25. I'm applying this symbol to it. I want you to do something to 25. I want you to take the square root of it, and then you do it, right? So that's what this d dx is saying. It's saying do the derivative. So now, given that's what that means, let's look at what they say. They're saying the constant multiple rule. They're saying that if you have some function and it's just being multiplied by some number, then when you apply the derivative, that number, that constant, just comes along for the ride. And I'll give you an example of that. Let's say that you wanted to dx the derivative of 5x squared. Well, as we know, you multiply by the 2 and subtract by 1. The 5 is just kind of hanging out. Nothing. You don't do anything with the 5. It's just there. So you could say the answer is 5 times 2x to the first. Right? The 5 is still just there, waiting to be multiplied by the 2 that is now present. The key thing is that when you take the derivative of a function that has a constant out front, that constant just comes along for the ride. And that's how I like to say it. The constant comes along for the ride. Of course, now you would multiply the 5 times the 2, and you get 10x as your final answer. But the key thing is you didn't do anything with 5. You just came along. The next one states that if you want to take the derivative of the sum of 2 functions, you have 2 different functions being added together, you can just take the derivative of the first function and then add it to the derivative of the second function, which is kind of nice. It's saying that you can just do one at a time. Another way of writing that then is you just say f prime plus g prime. These are all different notations that you would see. So whether you see d dx in front of f, that means the derivative of f, or if you saw f prime, as we know, that means the derivative of f. Works the same way with subtraction. So that's really plus or minus, plus or minus, plus or minus. The sum of 2 functions, the derivative of the sum of 2 functions is the sum of the derivatives of those 2 functions. Okay, the power rule, we've already seen, that's the biggie. d dx of x to the n is n x to the n minus 1. And we've also already seen these special cases. I'm going to write one of those special cases a little differently, but if you have d dx of a constant, now you notice that we're using the letter k to mean just a number, just a constant. I think I probably would have preferred the letter c, because c is the first letter of the word constant. But they're using the letter k because in a lot of contexts, k represents a constant. So the derivative of a constant is nothing, and the derivative of a constant times x is just a constant. Or the special case they gave is that the derivative of just x is just 1. But that's just a special case of the fact that like the derivative of 5x is 5. The derivative of 10x is 10, so the derivative of 1x is 1. So just make sure you know that. How's all this so far? We're writing down a lot of rules. It could be easy to look at this list of rules and get overwhelmed. But in fact, the only rule that we've really mentioned so far is the power rule, which we're all feeling pretty good about. These are just special cases of the power rule. And what we're really saying is about a constant, that a constant comes along to the right. And we'll see that in context. Okay, so there's two more functions that we want to know how to take the derivative of. And that is our exponential functions and logarithmic functions. So we can successfully ignore this rule because we don't come across any problems like that in this course. But we do look at the exponential function, e to the x, and we do look at the natural logarithm function, natural log of x. So first of all, let's all clarify what e to the x, so f of x equals e to the x, and f of x equals natural log of x look like. What are those functions? What does e to the x look like? First of all, what's e? Yeah, 2 point something. Very good. Like, so we all know the number pi, 3.14. E is another special constant in mathematics, and e is roughly 2.71828182 something. Goes on and on. So it's an irrational number. It's infinitely long, and it comes up a lot in application problems, where you look at natural growth rates, like the natural growth of bacteria or the natural growth of populations of organisms in general, or the natural decay of radioactive substances. E comes up in those problems. It's a constant that applies to natural processes in nature. Okay, so we have e to the x. This is just an exponential function. So what does any exponential function look like? You've got an asymptote over here, and then blasts up over there, right? That's why we call exponential growth, because it starts going up, and it goes up really fast, and it keeps going up even faster. So that's exponential growth. So then what is this function, natural log of x? It's what? Constant. It's not a constant. It is the inverse of the e to the x. Absolutely. It's the inverse. And technically what this is log base e. It's log base e. Normally we deal with log base 10, or we deal with log base e. So ln is really the natural logarithm, which means log base e. It's enough for us to realize that when we talk about e to the x, anytime you want to find the inverse of a function, you graph the diagonal line y equals x, and you reflect that graph across the diagonal line. And that is what the natural logarithm graph looks like. There. So that's the natural logarithm graph. They're technically inverses. I'm drawing that here to show you that e to the x and natural log of x are inverse functions, meaning that there are mirror images of each other across the diagonal line y equals x. And so that's what those functions do. E to the x is exponential growth, and the natural logarithm starts off quite steep. How steep? Asymptotically steep. And then it kind of, levels off and continues to grow, but not like the exponential growth. Exponential growth is crazy fast. Logarithm growth, logarithm growth is kind of fast. It's still increasing, but not super gigantic. Okay, so those are two functions we're interested in. The great news about e to the x, the derivative of e to the x is e to the x. It is a unique singular function whose derivative is itself. That's very rare to have a function that is its own derivative. Right, yeah. How does that work? Well, it's really interesting. What that states is that if you look at any point on the curve e to the x, like I'm just going to choose, let me do it this first. I'm going to choose the point 1. So x equals 1, and I go up here, and I look at the value of that coordinate. First of all, what is the y value? If I plug 1 in, e to the 1 is just e. So my y value is e, which is roughly speaking 2.71. Check out how cool this is. What does that mean? What is the slope at that point? Also e. So this is so cool. This is a function such that if you look at the y value of the given coordinate, like let's just say I choose the y value at 9. What's the slope right there? 9. Like, that's really great. This function is just so readable that no matter what y value you're looking at, that is simultaneously how steep it is right there. Isn't that kind of cool? So this is very unique. E to the x is one of the very, very, very few functions whose derivative is itself. I will challenge you to come up with another function whose derivative is itself. There is another one. And in fact, there's infinitely many of them, but it's kind of cheesy, the infinitely many. There's another one that is distinctly different from e to the x, and you can all figure it out. You all have the calculus power now to find a function whose derivative is itself. I'll say it. Let everyone have a chance to think about it. Okay, so that's the derivative of e to the x is itself. The derivative of natural log, so the derivative of natural log. Now, just so we all know, when I refer to natural log, that's the natural log of the x, the input. Okay, we normally call the input, right? We look at that and we say, hey, that's the input. But another way of referring to the input is the argument. The argument of the natural logarithm is the value that you plug in. So when we say the derivative of the natural log, the answer is 1 over the argument. I'll give a nice example of that. Yeah, I will. I'll give a nice example of that. Let's say that you had the function was natural log of x plus 5. Then the derivative would be 1 over the argument. So that's how I'm using the word argument. Argument is synonymous with input, unless you're talking with your spouse. No, I'm just kidding. Right. Well, so those are some extra rules. I would like to be able to tell you that those are all the rules you need for this class. I'd like to be able to tell you. No, we just have a few more rules. There are a few more, but these are the basics, okay? These are the basics. These are the fundamental rules of taking the derivative. Everything we do after that builds on these, but just in a building on kind of way. These are still the only basic rules we need to know. Okay, so these are what we'll get to eventually, but after our first test. So now, back to the question, the derivative of 3 natural log x. The answer is much easier than you would expect. First of all, what is this 3? It's just a constant, and it just comes along for the ride. So I can go ahead and start writing down f prime of x equals 3. And now all I have to do is just take the derivative of natural log of x. And the derivative of natural log of x is 1 over the argument, which in this case is 1x. Now we can clean that up. That's not what you would give to a friend. You would say f prime of x is equal to 3 over x. Oh, now number 7. Oh, of course I can. I think I hit it hard enough. A little more? No, I don't think so. All right, so we've got this nice looking derivative here. By the way, is this the last problem? Is this the last problem for today? Oh, no, there's more. Oh, geez, I have to go to the next slide. Okay, so here we have -2 root x minus 8 over x to the 5th. This is a great example of how, when you're given a function, this is written in clean form. You're not ready to do the derivative on this yet. What do I have to do to both of those to make it better? So we're going to rewrite it. Remember, this is the first step where you just rewrite something, and you're rewriting it in a way that you can do the power rule. So root x is actually, x to the 1/2. And x to the 5th in the bottom is actually -5th in the numerator. Okay, so there you go. So now we've taken our function. It was written in clean form, not calculation form. We rewrote it into calculation form. Now we do the power rule. So 1/2 times 2 is 1. X to the 1/2 minus 1. Who remembers how to write -1? Minus 2/2. Yeah, so there we go. So now that's x to the -1/2. And then -5 times -8 is positive 40. X to the subtract 1, that's -6. Is what one negative? Oh, that is negative. Thank you so much. I dropped my negative. I dropped it. Okay, so now we're all here. So now this is the derivative. So you would want to have that labeled as such, f prime of x. Now our next step is we have to clean that up. So we're going to write it in clean form. So first of all, x to the -1/2. What does a negative exponent mean? You drop it down, push it down to the bottom. So now I have -1 over x to the 1/2. And then I have plus 40 over x to the 6th. Well, there's one more thing we have to do to write this clean. Yeah, that's really the square root. If you had already done the square root, then that's fine. I tend to break it up into as many baby steps as possible because I want my audience and my brain to know what I'm doing. So better to have more steps to get to your clean answer than fewer and get wrong. Okay. What can we say about calculus work? Okay, it's weird. Is it a couple steps or lots of steps? It's a lot of steps, and that's why it gets a bad name, right? Are the individual steps hard? Was it hard to rewrite root x as x to the 1/2? That's not hard. Is it hard to bring x to the 5th up to the numerator? It's not hard. Is the power rule hard? No, that's not hard. You multiply and subtract. Is it hard to drop a negative exponent back into the denominator? No. Is it hard to turn a 1/2 into the root? No, none of these things are hard. But you know what it is? It's a lot. It's a lot to think about. It's a lot to hold in your mind. It's a lot to do one step at a time and make it all look good. Okay. Any questions? I forgot that I need to know. What's the next problem? Oh, so go ahead and write these things down. Oh, okay. Well, use the product rule. Where did I? Oh, and then I theoretically wrote this down. Oh. I clearly do not have the correct slide right here to do this with. And so the number 12, that's on. Oh, well, actually, so there's only one thing I need to do, and that's write down the product rule. And then number 12. Okay, so I am right here. I'm right here with you. These are the problems. Okay, now, silly me, I don't know that I'm putting the product rule on the test. Part of me thinks to myself, geez, if this is not on the test, we shouldn't do it right now. Let me verify. Right? I mean, how do the rest of you feel? I mean, if this isn't going to be on the test you're taking on Tuesday, should we do it or should we not? Yeah, I mean, part of me thinks we should wait, but let's just take a look here. My test goes through. Oh, yep, no, sorry. Sorry to get your hopes up. No, we are doing the product rule. Yeah, which is okay. It's not bad at all. Okay, let's do it. All right. And what, we got into 30 minutes? Okay, we can do this. So the product rule. The product rule states, what if now notice we only talked about what if you're adding two functions together. What if you multiply two functions together? This is a very different and unique situation. So I'm gonna come back to do number 12 in a little bit here. Gosh, what should I put myself? I'll do it right here. So let's say that you want to take the derivative of the product of f times g. I'm gonna write it like this, and I'd like you to write it like this too. So we want to take the derivative of the product. Now, what would be wrong, okay, would be to just take the derivative of each. Okay, that would be the intuitive idea. You might look at that and say, yeah, that seems reasonable. If you want to take the derivative of f times g, just take the derivative of each one and then multiply them together. Unfortunately, that's just incorrect. It doesn't lead to the right answer. So I just wanted to say right up front, that's the incorrect solution, even though that's intuitive. In fact, if you want to take the derivative of a product, now the first thing we're going to do is you're going to set up the solution with parenthesis, parenthesis, plus parenthesis, parenthesis. This is always how we're going to do it. So instead of just being one product, it's actually two products that get added together. And this is what it looks like. It is the derivative of the first times the second plus the derivative of the second times the first. What? Oh, yeah, because here it's f prime regular g, and then g prime regular f. This is the actual product rule, which is pretty surprising because again, intuition, we might just want to say take the derivative of each and just write it down, f times g prime. But in fact, it's not that. It's f prime times regular g, and then g prime times regular f, and you add the two together. So the product rule for a derivative states that when you're taking the derivative of a product, you actually do The derivative of the first times the second plus derivative of the second times the first. That's worth memorizing. So I'd like you all to repeat after me. Derivative of the first, derivative of the first times the second plus the derivative of the second times the first. Now let's try that again. Derivative of the first times the second plus derivative of the second times the first. There we go. So that's our product rule. I will give that to you on the test. Okay? But you have to be able to know what to do. But I am going to give you that formula. So now that you know the product rule, let's go ahead and try it. So we have this function here, f of x equals a little polynomial being multiplied by an exponential function. So here's what I'd like us all to do. You're going to write down f prime of x, and you're going to write parenthesis, parenthesis, plus parenthesis, parenthesis. That's always the structure of the product rule, so you might as well write it down right up front to remind you what you're about to do. And in fact, if you really wanted to, you could even write the product rule on top. You could even label all this. This is f and this is g. Then this would be f prime g, g prime f. You know, what a great idea to create the structure that you need to plug in the parts and to even label it. So what's the derivative of f? What's the derivative of the first? I'm just using the power rule. Yeah, does everyone agree? Is that the power rule? Negative 48x to the 7th plus 15x to the 4th. Does it work? Okay. And then we just write down the second one. It's just 7 e to the x minus 1. No work. We just write it down. Now, the derivative of the second. Let's consider this separately, okay? What's the derivative of e to the x? E to the x. What's the derivative of 7 e to the x? Remember, the constant comes along for the ride. So the derivative of 7 e to the x is 7 e to the x. What's the derivative of 1? Nothing. Exactly right. So the derivative of 7 e to the x minus 1 is 7 e to the x. Because the 7 comes along for the ride with the e to the x, and the derivative of a constant is nothing. Okay, so the derivative of second times the first. So that's negative 6 to the x to the 8 plus 3x to the 5th. So what do you notice about using the product rule? For each pair of parentheses, you're only doing work half the time. Like I did this derivative, I just wrote down what was there. I did that derivative, I just wrote down what was there. So you're still only actually taking two derivatives, right? You're only doing the derivative twice. And then you're just plugging in what the original formula had. Now, I want you to know that's already the answer. That's the answer. Sometimes I'm going to ask us to simplify. Sometimes I'm not going to ask us to simplify. I think for this first test, I'll be happy if you simply demonstrate to me the product rule. That's the product rule. Let's try it again. We have this product now. Again, you can label it if you like. There's the first function, there's the second function. And so when we go to write down the derivative f prime of t, notice now that we're in the variable t, we're going to use the product rule because it's a function times a function. And I'd like you to go ahead and just set it up as parenthesis, parenthesis, plus parenthesis, parenthesis. Because that's the form of the product rule. Derivative of the first times the second plus derivative of the second times the first. The more times you say that, better. Like go home tonight and say it a whole bunch of times. Like just walking around your house saying it. Your roommate, your spouse is like, what are you saying? Don't worry about it. Doing calculus. Okay, so derivative of the first. What's the derivative of the first? The derivative of t squared is 2t. The derivative of 4t is 4. The derivative of 3 is nothing. So derivative of the first times the second. You just write it down. And then derivative of the second. So what's the derivative of 7t squared? 14t. Derivative of 3, nothing. Times the first. T squared plus 4t. Need to make my parentheses bigger. Plus 3. Okay, that's already the answer. What? Right, and they would want us to plug in 3 at this point. Now, keep in mind this product rule that we just did. This one you can simplify. I mean, we could have simplified this one too. You'd have to do FOIL, right? Like up here, we'd have to do FOIL, first, outer, inner, last. Here, we would just have to distribute. And then it'd be a matter of gathering up all of your like terms and simplifying. A little messy with the e to the x, and that's why we didn't do it. This one, could you simplify it? Could you FOIL? Could you distribute? Could you combine like terms? Sure you could. Again, I won't require it. I just want to see you do the product real quickly. But yes, now we would plug in 3. So, and a lot of this you can do in your head. So like 2 times 3 is 6, 6 plus 4 is 10. 3 squared is 9, 9 times 7 is 63, 63 plus 3 is 66. 14 times 3 is something. Is it 42? And then 3 squared is 9, 9 plus 36 is 45, 45 plus 3 is 48. So you have all of that now, which again, you can do some of this in your head, 660 plus something. I don't need a calculator for that.
So 42 times 46.
2016 plus, yeah, a lot, plus 660. You don't think so? Did I mess it up? 3 squared plus 4 times 3 plus 3. You're right, it's 24. I messed it up. Okay, so that's actually 42 times 24 is 1008. And then that plus 660 is 1668. Okay, so now what did we just find out? 1,668 what? Units of what? What is that number?
It's the origin of f prime.
Well, it's the coordinate of f prime, and it's the slope of the original graph. So what we're saying is that this original graph right here, now watch what I'm about to do. I'm going to show you how to make a little sketch. This is a little sketch. Now, if I knew where 3 was, so 1, 2, 3, first I'd have to find the coordinate for where 3 is. I'd have to plug 3 into all that, which I suppose we can do because we have that information already there. This part was 24, and that part was 66. So the coordinate is 1,584. So way up there, there's the actual coordinate. And what is the slope right there? Very steep. The slope is 1,668/1. So notice what we found out. On this particular function, at the coordinate 3, 1584, the slope is up 1,668, right 1.
How do you find the original function from the derivative?
How do you find the original function from the derivative? Like if I just walked up to you and I handed you the derivative, how would you find the original? You would do an integral, which is what the second half of class is all about. Yeah, derivatives and integrals are opposites. So if you take a function and do the derivative, you can take the derivative and do the integral, and you get right back to the original. Yeah, it's a very nice, clean process. Okay, very nice, folks. Let's try. Do we have another product we'll try? Yes, we do. Now this one I will simplify with you because it turns out to be nice. So we have this function here, and it is a product, right? It's that polynomial times that e to the x. So as before, we'll begin by writing g of x, g prime of x is parenthesis, parenthesis, plus parenthesis, parenthesis. And if you want to label, you can. That's our first function. That's our second function. And so we're going to do derivative of the first times the second plus derivative of the second times the first. I think it's very helpful to set up the product rule like that. All your parentheses ready to go. You've got it labeled. Now you know what to do. So what's the derivative of the first? Is it 2x plus 1? The derivative of x squared is 2x. The derivative of x is 1. And the derivative of 2 is nothing. Okay, so the derivative of the first times the second, so that's e to the x. And then the derivative of the second, what's the derivative of e to the x? E to the x times the first, so x squared plus x plus 2. Okay, now, as I said, this is the product rule. That is the answer. That is the derivative. But this can be cleaned up considerably. What do you see that we can do with that e to the x? Well, yeah, I mean, they're kind of combining. That's a good way of saying it. Another way would say that you could factor the e to the x out front. Each expression has an e to the x. So I bring the e to the x out front, leaving behind 2x plus 1 plus x squared plus x plus 2. So I basically just factored the e to the x out. And then that allows you to combine like terms on the inside. So combining like terms on the inside, I've got x squared plus 1x plus 2x is 3x plus 1 plus 2 is 3. And that looks really good. So there are times when a function simplifies nice, and other times when it doesn't simplify very nice. This one simplifies nice, and that's a trick we're going to use over and over. It is when you take the derivative of a function with e to the x, you can often pull out the e to the x, or even other times, when you just end up with the same chunk in both parts, you might as well factor that chunk out and then combine what's left. How does everyone feel about the product rule? So you can see why I said earlier that these are like the fundamental rules. You know, the individual, how do you take the derivative of that and that and that? Whereas the product rule is kind of a combo rule. So we have derivative of e to the x is just e to the x, and the derivative of natural log of x is 1 over x, and now the derivative of f times g is derivative of the first times the second plus derivative of the second times the first. Okay, so that's the product rule. Again, I will give you the formula, but you should work on memorizing it. So that's the product rule. What other kind of rule should you expect? Quotient. So that's if two functions are being multiplied. We also have a rule if two functions are being divided. Now the division rule can feel a little more, a little longer. I'm going to write it down first. d dx of f over g. Now first of all, there's a lot of commonality between these two rules, except we say it very different. Okay, so first, I'm going to write this expression, except I'm going to reverse the order of g f prime, and then instead of plus I write minus, then I'm going to switch those two, f g prime. So that's fairly similar, just change it around a little bit. You'll notice it's still the same, it's the derivative of f and g, and it's still the derivative of g and f, except it's minus instead of plus. And then on the bottom, it's just g squared. Might feel weird. Oh, g squared. Then you square the g function. So that's the quotient rule. I'd like to go ahead and teach you a little mnemonic that I've always used my whole life. I think it's cute. That's how I always remember it. And that is, you can say this one of two ways. You can call this high and low, and in which they're referring to the numerator and the denominator, so the high and the low. Or I always learned it as high ho. Like hi ho, hi ho. Is that forward we go? You know the old Disney. Okay, so when we talk about high low and high ho, what we have here is, okay, everybody gonna watch me do this here? Ho, d high, meaning the derivative of the high one, minus high, and then d ho, as in the derivative of that one, all over ho times itself, ho ho. So what I've always heard, and this is what I learned in my calculus class, was ho d high minus high d ho all over ho ho. And that's still to this day how I do the quotient rule. Ho d high minus high d ho all over ho ho. So everybody try saying it. Ho d high minus high d ho all over ho ho. Yeah. Now ho ho, I think, you know, Santa Claus, ho ho ho. Some people have been like, well, you shouldn't say this one because of ho. That's a mean thing to call someone. Well, that's true, but I'm not referring to that ho. I'm referring to Santa Claus. Ho ho ho. Okay. I was a young innocent child when I learned this. I didn't even know there was another interpretation of ho. Okay, or you can say high d low. So this could be low d high minus high d low all over low low. So it's totally up to you how you want to say it. But this is the rule. So let's go ahead now and try it out. So I've got my quotient rule. Once again, we should set it up so that we're ready to plug everything in. So I've got my f prime of x. And what is the structure we're looking at now? It's parenthesis, parenthesis, minus parenthesis, parenthesis, all over parenthesis squared. Now I'm a big fan of writing down formulas empty. This is what I call writing the formula empty. It's a great best practice because now it's just a matter of plugging in all the pieces, and you've freed your brain up to be focusing more on the derivatives you're about to do rather than worrying about where everything goes. So again, what we have here is ho d high minus D hope, all over the whole hope. Where again, I'll go up here, I. Up. Okay, so now we just start filling everything in. So ho, that's x to the fourth. D high, and D high means derivative of the top. So what is the derivative of the top? Yeah, 35x to the fourth. I obviously did not leave nearly enough room. There. Plus 32x cubed. Still did not leave enough room. Minus 9x squared. Oh, that'll teach me. Okay, so you need much bigger parentheses. So far, everyone agree that's ho D high, low D high. You can see this sounds a lot better, ho D high minus high ho over ho ho. If instead you were saying denominator derivative numerator minus numerator derivative denominator, it would just be a mouthful. Okay, now high. So obviously I need bigger parentheses. What was I thinking? So high is just writing down itself, 7x to the fifth plus 8x to the fourth minus 3x cubed. D ho. So what's the derivative of the bottom? Is 4x cubed. So the derivative of the bottom is 4x cubed. All over ho ho. Now you notice in the bottom, there is no derivative. The denominator of the function stays the denominator of the function. It's just that now you're squaring. So that's pretty interesting to notice. That we're taking the derivative of this function, and yet the denominator, you don't actually take the derivative of the denominator itself in its place. It's actually getting squared. Whereas in the numerator, you'll have both the derivative of the numerator and the derivative of the denominator multiplied and subtracted together. All right, well, folks, that's the quotient rule. And again, I would be very satisfied just to see you apply that correctly. Sometimes it's simplifiable, sometimes it's not simplifiable. Just for fun, we'll simplify this one. And when I say fun, well, you can have your own feelings about that. So let's distribute. We're going to distribute x to the fourth to the first fifth. So big fraction line. That'd be 35x to the 8th plus 32x to the 7th minus 9x to the 6th. And now we're going to distribute a negative 4x cubed. Everybody watch what I'm about to do here. I have a negative in front of all this, and I'm multiplying 4x cubed. I'm just going to go ahead and move that negative to my 4x cubed and distribute it. So I'm really distributing a negative 4x cubed all this now. I hijacked my minus, put it on the negative 4x cubed, and now I'm going to distribute. So now what do I have? I have negative 28x to the 8th minus 32x to the 7th plus 12x to the 6th. All over x to the 4th squared. What rule do we use for x to the 4th squared? X to the 4th squared. Do you add or multiply? You do multiply. Because x to the 4th squared is really x to the 4th times x to the 4th. And how many x's are being multiplied? 8. All right. Looking good. So now I can combine a lot of terms, can't I? See, this is actually going to simplify down really nicely. Like, really nicely. So I have multiple x to the 8th terms. So 35 minus 28 is 7x to the 8th. And then I have multiple x to the 7th terms. In fact, my x to the 7th terms cancel out. You know, if I did that right. And then negative 9x to the 6th and positive 12x to the 6th, that's plus 3x to the 6th. All of that is over x to the 8th. Now what? Yeah, you can think of it in one of two ways. In the top, you can factor out x to the 6th, or you can rewrite this one fraction as two different fractions, putting each numerator part over the denominator. That's what I'm going to choose to do. So this is 7x to the 8th over x to the 8th, and then plus 3x to the 6th over x to the 8th. And now you get to cancel a lot of x's, don't you? Like in the first one, all the x's cancel out. So you just have 7. And then in the second one, if you cancel out 6 x's on top with 6 x's on bottom, what do you have? If you cancel out 6 x's on the top and from the 6 x's on the bottom, you only have left over 2 x's on the bottom. So it's x squared. Now, did this follow the rule of it gets worse before it gets better? For sure. Yeah, got a little hairy there in the middle. but it turned out to be pretty clean when we were done. I think I'll do one more. Yeah, one more quotient rule with you. Yes, Henry.
So there's like an example on the quotient rule write down. And says try it like 2 ways.
Oh yeah, I said 2 different ways. Okay, I'll show it to you. So in this one, what could we have done first? Now notice what I did at the very end. I split this 1 fraction into 2 fractions. What if I take my original problem and split it into 7x to the 5th over x to the 4th plus 8x to the 4th over x to the 4th minus 3x cubed over x to the 4th. What could we have done immediately? Those are gone, so that's just an 8. What did I do here? That one, and then what did I do here? What's the derivative of 7x? What's the derivative of 8? Nothing. And then the derivative of this we have to do. Okay, so a little scratch work, that'd be minus 3x to the negative 1. Multiply, that's positive 3x to the negative 2. Push it down to the bottom, 3 over x squared. What answer did we get? Right, I figured you like that way. Because I wanted you to see the quotient rule. and even more importantly, I want you to see the quotient rule works. The quotient rule works. So we'll just do one more. I wasn't trying to abuse you. Okay, so this one, we're going to do high-de-ho. Wait, so this high, so using mnemonic now, f prime of x, and setting it up. So again, big fraction line, O d high minus I d o all over O. This one cleans up nicely too. So O d high. What's the derivative of 4x plus 3? It's just 4. The derivative of 4x is 4. The derivative of 3 is nothing. Minus high d ho. The derivative of 2x plus 2 is 2. Over ho. 2x plus 2 squared. All right, now this, again, is going to clean really nicely. So distributing the 4 to the first parenthesis, that's what? 8x plus 8. Distributing the 2 to the second parenthesis, but again, keep in mind that's a minus. So I'm going to move my minus to be on the negative 2. That way I have negative 2 being distributed. So that's minus 8x minus 6 all over 2x plus 2 squared. What do we get to do in the top? We're going to cancel those 8x's. Again, gets worse before it gets better. Lots of cancellation opportunities in calculus. And we just have 2 over 2x plus 2 squared. That's the derivative using the quotient rule. Now you notice they also want you to plug in 1. So we would say f prime of 1 is just 2 over, 2 times 1 is 2, 2 plus 2 is 4, 4 squared is 16. 2 over 16, which is really f prime of 1 equals 1/8. So at that coordinate, the slope is up 1 right 8, up 1 right 8, up 1 right 8. I'm hoping that leaves us at the end. Let me just see here. The next problem, you can try 17 on your own, but you can cross out number 18. So try 17 for homework. I suppose what I could do is just check to see. Is that one on the test? Oh yeah, in fact, you definitely want to do 17 because there's a problem like it on the test. Now, this took us up to the end of class. We have 2 more minutes. I'm wondering, yeah, I gave you a reference sheet on the test. So it has all those rules. There's one more problem that we should do together. 2 more problems actually. But darn, I'm kind of out of time. Let me see if I have my practice test up there. Oh, yeah, this is the practice test. So the practice test problem that I really like to do with you. You know, I might be forced to simply turn this problem into extra credit because I realize I'm out of time, but I want to do it with you. Yeah. So this problem right here, it's a really good problem. I think it's only fair that I simply make it extra credit. But everybody, can we do it together right now? You have to leave, I understand, but it does go very quickly. And we still have 1 minute. So no matter what, do 1 minute with it. All right. So we're looking at a cubic. The graph of this cubic has 2 horizontal tangents. Everybody, first of all, just go ahead and draw a graph. A cubic, a cubic just goes like this, but it could wiggle in the middle. And in fact, this one goes like this. So it goes down to infinity, up to infinity. That's what our cubic looks like. So the graph of this cubic has 2 horizontal tangents. What does that mean, a horizontal tangent? Yeah, it's got 2 0 points. There's one, m equals 0. And here's the other, m equals 0. This is a kind of problem that we'll do over and over in this class. So yeah, I can make a bonus for the first test. So they're saying one occurs at a negative value of x. Sure enough, there it is at a negative value. And one occurs at a positive value of x. So one is over to the right of the y-axis, one is to the left of the y-axis. Find both. So on the one hand, you can just graph it and find it, right? You just go to decimals and find those. Find the minimum point, you're looking for the minimum coordinate, and you're looking for the max coordinate. That's it. So here's what we would do. We want the 2 points where the derivative is 0. So you take your function. What we're doing right now is a general procedure we'll use over and over. And what you do is you take the derivative. So that's just 6x squared plus 24x minus 126. You take the derivative, and so now this thing now represents slope. This is the slope of our whole graph. And what do we want our slope to equal? 0. We want to know when is that slope going to equal 0. So you set it equal to 0. And now this is what you're solving. And as soon as you solve that, you'll have the 2x values. So this is just a very basic factoring problem. We can all divide out a 6 just to make the problem easier. So now we have x squared plus 4x minus 21. And we can all factor that. What do you multiply to make 21 that adds to make 4? What do you multiply to make 21? Yeah, it's going to be 3 and 7, so it's going to be x plus 7, x minus 3. That's our factoring job. So then you set both of those equal to 0. And you say either x plus 7 equals 0 or x minus 3 equals 0. And so x equals negative 7. That's my negative x value. Or x equals 3. That's my positive x value. So what did we just do? We took our function, we took the derivative, and set it equal to 0. That was our way of saying, show me where the flat spots are. Take the derivative, set it equal to 0. Show me those parts of the function where the slope is equal to 0. We divided by 6, we factored it, we found the 2 points, negative 7 and 3. And so I automatically know that those are flat spots. And now all I need to know now is just the coordinates. So how do I find the coordinate when x is 3? Plug it into the original. And then how do I know the coordinate when x is negative 7? Plug it into the original. So you would take your function, and we would go ahead and do 2 times, what is it, 3 cubed plus 12, 3 squared, 6 times 3, plus 17. The first coordinate is at negative 199. So that coordinate right there is 3, negative 199. And then this coordinate up here, I would now change my 3 input into negative 7. And that's 801. So this coordinate is negative 7, 801. That's the whole problem. I realize I rushed through this problem. Class is over. Probably got to go. But just read the question again. It says the graph of this cubic has 2 horizontal tangents. Yes, it does. One occurs at a negative value of x and the other at a positive. Yes, it does. Find both coordinates. Negative 7, 801, 3, negative 199. That's the problem. So I'm going to leave that one on the test as extra credit. There's bonus. Now, immediately right now, I'm going to sit down at my computer and post the answer keys to the practice test. So when you go home this weekend, do the practice test, look at the answers,